This video also belongs to the book Statistical Modeling with R that I published with the Oxford University Press in 2023. In this video, I would like to talk about the large issue of model selection and start by stating the basic problem, then mention the principle of parsimony, which is the conceptual basis that is used to select models, then talk about a model selection in the frequentist framework, and then in the Bayesian framework, in order to complete the current ideas of model selection in the Bayesian framework, I need to talk about the posterior predictive distribution and the PP checks that we are going to use in coming videos. That is the basis of the current views of model selection in the Bayesian framework. That is the final point in this video. So the basic problem of model selection is that scientists often compare several alternative models to explain the same data sets. These alternative models could be either reflect separate scientific hypotheses. For instance, the response variable is explained or determined by explanatory variable X, and the alternative model could be, for instance, that the response variable is explained by the addition of the effects of variable x1 and x2. Sometimes these models could also arise as plausible alternatives in the sense of exploring which model could actually fit possible data and to generate hypotheses to be tested by specific scientific experiments later on. So whenever we are in the context of model selection, we need a criterion to choose the best model out of a set. So the only one criterion valid for the general linear model is to choose the model with the highest R-square or percentage of variation explained. The problem is that the R-square in the general linear model always and only increases with model complexity. This means that even if you add irrelevant explanatory variables that are irrelevant with respect to the response variable, the resulting model can only have a higher R-square than a previous model without this nonsensical value. So two fundamental problems that arise as extreme cases. One is the problem of overfitting, that is ending up with an overly complex model that tends to fit the noise, that is the variation, and that is too sensitive to minute details in the data. As a result of having too many parameters, these parameter estimates are very imprecise, and predictions are out of the data set that was used to build the model are often nonsensical. In the other extreme is underfitting, that is, we ended up with an overly very simple model that is robust and insensitive to tiny details of data that fails to reflect the general trends of this data. So the principle of parsimony is a conceptual pillar of model selection in statistics, and the idea is that this principle should lead to a model with the smallest possible number of parameters for an adequate representation of the data. The conceptual basis of this principle has a long, colorful, and convoluted history, in that it has been generally and wrongly attributed to a Franciscan monk in the 13th century, William of Ockham, who wrote in Latin, now translated into English, that all things being equal, the simplest solution tends to be the best one. The principle of parsimony is used as a heuristic guide that should lead to the simplest, not necessarily the correct statistical model that is consistent with available evidence. So model selection in the frequency framework is based on the use of the WAIC information criterion, the AIC, which is by far the most frequently used metric of model selection. Its conceptual basis lie in information theory, which is one of the products of the Second World War in the hands of Claude Shannon, one of the geniuses of the 20th century, and in a distance proposed by Kullback and Leibniz in 1951, and this distance measures the disparity between the true generating model and a given statistical model. So intuitively, the smaller this distance, the closer is the model is a given statistical model to the truth, or at least the true generating model. So Akaike found a relationship between this distance, this Kullbaum-Leibniz distance, and the log likelihood of a fit statistical model. This relationship is actually crystallized in the equation of the AIC, which is very simple. The AIC is twice the log likelihood of a model plus 2 times the number of parameters. The stronger the support of an empirical model to the data, the lower the AIC of a model, which leads us to prefer the model with the lowest AIC in a set. So in order to complete the operationalization of this AIC, I need to introduce a key feature to be discussed in further detail in coming videos. And this feature is the criterion of the deviance. The deviance is a general criterion that is to be minimized when fitting a generalized linear model in video 12. This was introduced by Neller and Wedderburn in 1972. So the deviance is defined as the difference between the likelihoods, the difference in log likelihood between the saturated model, a model with a perfect fit to the data with as many parameters as data points in the data, and the current model. So deviance is analogous but not identical to residual deviation. That is, we want to minimize deviance, that is to minimize the distance or the difference in log likelihood between the perfect fitting model and our current model. So putting them into a scheme, we can conceptualize 4 models. First, the null model, in which has a single parameter, that is, which is the mean, has no explanatory variable. This is called the null model. Then we have at the other extreme the saturated model, that is the model that has as many data points, as many parameters as data points. This is the saturated model. And then let's say that we have 2 models, M1 and M2, whose likelihoods are lig1 and lig2. So the deviance is the difference between the deviance of model M1 is the difference between the likelihood of this model and the likelihood of the saturated model, and the deviance of model L2 is the difference in log likelihood between its log likelihood and the likelihood of the saturated model. So if we compute the difference of deviances between these 2 models, this corresponds to the delta AIC. The delta AIC of models M1 and M2 is the likelihood ratio, the ratio of the likelihoods of these 2 models plus the difference in parameters. So fitting the models M1 and M2 requires to minimize their deviances, and we can calculate the delta AIC, the difference in AIC, to compare the 2 models. This is what matters. The absolute value of the AIC is completely irrelevant. It can even be negative. So what matters is the difference of AIC between candidate models in a set. So the 2 components of the AIC change in opposite direction as model complexity increases. As the model becomes more complicated by having more explanatory variables or interactions, the deviance declines, that is, the goodness of fit increases, but the number of parameters increases. So the 2 components in the equation of the AIC change in opposite directions. So in contrast to the R squared, the contrasting changes in the 2 components of the AIC prevent overfitting and yields a balance between these aspects when selecting models. So what matters, I repeat again, when comparing 2 models is the difference of the AIC, not their actual values. So the difference of AIC greater than 2 has often been used as a threshold to select a model. One of the key references in this area of model selection by Burham and Anderson stated in a lawyer-like expression that as a rough rule of thumb, models with a difference of AIC of 2 units both have substantial support and should receive considerations when making inferences. So the rule of the delta of AIC greater than 2 units to compare models in the frequency framework is completely arbitrary, and as arbitrary as the significance criterion of 0.05 in hypothesis test. So use it with care. So 3 important remarks to close off. So first, model selection is different from hypothesis test. In model selection, a statistical model is never rejected, but only said to have a lower empirical support from the data compared to other models in the set. The second point is that the selected model may have terms that are not statistically significant. The goal of model selection is not to erase non-significant terms from statistical model. So we should bear in mind that we may well end up with terms that are non-statistically significant, and this is not a mistake. The third point is that instead of selecting the more parsimonious models, we may opt to generate the average model. The average model is the average model in a set of models. So this average model contains parameter values that will combine the estimates of the parameter estimates of each of the models in the set under AIC weight. I direct you to my book or other books for details on how to carry out the formulation of the average model in a set. In the Bayesian framework, 2 information criterion has been proposed: the Bayesian information criterion and the deviance information criterion. One in 1978 and the other in 2002. So both the equations of both criterions are very similar to AIC, a model related to the model goodness of fit, and the other reflecting the model complexity, and both terms in each of these criteria vary in opposite direction as in the AIC. So the Bayesian information criterion has been dismissed by not being insufficient, for being insufficiently Bayesian, and the DIC has been shown to provide inconsistent estimates of the effective number of the parameters for some models. It assumes Gaussian posterior distributions, which is problematic with for parameters that has strict bounds, such as variances and correlation coefficients. So the WAIC, the Watanabe-Akaike information criterion, or the widely applicable information criterion, if you don't like Japanese last names, seems to solve these limitations. So it is, but these are the WAIC is based on the posterior predictive distributions, which is why I need to make a detour to explain the posterior predictive distribution and then to return at the end of this video to the WAIC. So the posterior predictive distribution is the posterior distribution of new values of the response variable that is conditional on the data and the parameter posterior distributions, which in turn depends on the prior distributions and the likelihood of the fitted model. This idea is relatively old, dating from 1984, but has only been put to use very recently in the statistical practice. So the posterior predictive distribution contains a set of values of y that could have been generated by the fitted Bayesian model. It could have been obtained from either the current data or new values of the explanatory variables. So let's assume, for the sake of an example, that we have a response variable that has a Poisson distribution with a single parameter mu, the mean of the response variable. So the fundamental Bayesian equation for parameter estimation is that the probability, the posterior probability of the parameter given the data is proportional to the likelihood of the data given the parameter times the prior of the parameter. So if we include the new values, these new values, w underscore new is another unknown, we introduce them in the left hand side of our equation and in the correspondingly in the right hand side. So this is nothing substantial, nothing different or hard. But the current data cannot possibly depend on new data. The other way around, yes, that is true, but not the current data cannot depend on the new data, which allows a simplification that I'm going to show in the next slide. So the joint prior probability of the new data and the parameter can be decomposed as a product of the conditional probability, the following conditional probability: the probability of new data given the parameter times the probability of the parameter, and therefore the simplification that we carry out and the introduction of this the last equation into our previous one provides the following. And we notice that here we have essentially the posterior distribution as usual. So the posterior distribution of the new data and the parameter given the data is proportional to the usual posterior distribution and this prior. So we obtain therefore this following what I have here in between blue rectangles is the posterior distribution, and so we need, in order to obtain the probability of the posterior for the new data, we need to integrate, that is, we need to sum over all possible values of the new parameters in order to obtain a badly looking equation, which is the following. So this is the probability of the posterior of the new data and the parameter given the data is the following, and this let's recall that this integration sign simply means that we are making an infinitesimal sum, and this infinitesimal sum of these two products is done for all possible values of the parameter y. So this the numerical integration is carried out easily in common software and provides the posterior predictive distribution of y. Based on this posterior predictive distribution, we can formulate what they call PP checks or posterior predictive checks that are extremely useful and powerful ways of assessing the capacity of a model to generate observed features of the data. But let's first have some intuition about this threatening looking equation of the posterior distribution of the new data. So let's write the equation again. So let's assume let's show the following. This is the posterior distribution of the parameter y. So this is showing different values of y, of the mu of y, sorry, and it's a posterior distribution that was obtained by after using applying some Markov chain Monte Carlo. Let's assume magically, instead of an infinitely large number of values of mu of y, let's take just 4 of these values. Let's take the values of 0.9, 1, 1.2, and 1.3. If taking this value of 0.9, this is the probability density of the planned count, our response variable. So if the mean was 0.9, so this is the probability of obtaining 0, 1, 2, 3, and 4, and 5. The same for the other. So we have these profiles that show us the likely values of the response variable given the parameter 0.9, 1, 1.2, and 3. So the posterior predictive distribution, so each of these 4 posterior values of y predict the probability of obtaining each of the observed sets of values of the response variable. So not all these values are equally likely. 0.9, the mu of y 0.9 is very unlikely. The mu of 0.1 is very likely, the mu of 0.2 is even likelier, and the mu of 1.3 is less likely. So what we do is that we obtain here the posterior distribution is the weighted sum of these profiles by the probability of obtaining each of these values. So it's a sort of an average, if you wish, or if you prefer. So if we have k values of our response variable, the posterior predictive distribution would be a matrix of k row, and say if we want 1000 or 5000 or whichever number you want, columns, each of which is a potential distribution of values of y that could have been generated by the model parameters, posterior distribution, and the explanatory variables. So these are the k values of a response variable. This is one of the posterior distributions that could have been generated. This is another. This is the 1000th posterior distribution that could have been generated out of the same data. So we can calculate a given statistic, any statistic you wish, the mean, the standard deviation, the quantile, the ranges between the maximum and the minimum, the ranges between the quantile 97 and the quantile 13th, anything you wish. For each column of this 1000 potential distribution that could have been generated from the data, and therefore we obtain a distribution of 1000 values of the statistic of choice. We then calculate the same statistic out of the observed data, and we can actually use the PP checks to assess whether the model can predict on average, as a common and typical prediction, an important observed feature of the data. This is going to be used in coming videos when we fit more complex Bayesian models to the data. But now let's return back after seeing what the posterior predictive distribution is. Let's go back to the model selection in the Bayesian framework. Recalling the ideas of the DKL distance, Gelman and collaborators suggested to estimate this distance with the expected log pointwise posterior distribution. Expected means a kind of average. Okay, so this is a kind of average of the posterior predictive density of the new values for each data point. We sum them up given the current data. And so the WAIC is operationally defined as this expected log pointwise posterior distribution plus 2 times PWAIC, which is the effective number of parameters. So the larger this value, the poorer the fit. And the effective number of parameters, one of the ways of estimating this is is using the variance of this posterior pointwise log posterior distribution. So the WAIC is currently the preferred model, as far as I can tell, using in Bayesian model selection. But in fairness, it seems to me that this is an area where there is a lot of work in progress, and changes, refinements, and adjusted are to be expected in coming years. So the WAIC is asymptotically equivalent to the leave one out cross validation. This idea of the leave one out cross validation is to fit the model, obtain the parameters, extract one of the points, one of the rows in the data set, refit the model, and try to predict all the values of the k points based on the model fitted on k-1 points. So all these cross-validation ideas are very old, and they're typically too computationally intensive, because it means, as you may realize, that if you have k points, k being, for instance, 1000 points, you need to refit the model 1000 times, taking out 1 point at a time. So this is very impractical for large data sets. So the practical use of these cross-validation ideas, to which the WAIC is asymptotically equivalent, they all require some clever computational trick. So Vettari and collaborators created a package called LU, which is an acronym for the leave one out cross-validation, and of course, as everyone knows, is how the British call the toilets. So it's an irresistible acronym. So the trick that they implemented is called the Pareto smooth importance sampling. Okay, details about this, the theories are very involved, at least for me, and I explained in some detail in the book to which I refer you. By so doing, this package loop creates a metric of influence of each value on the predictive ability of the model, and this is analogous to the Cook distance that we have been using in the frequentist framework, and we are going to use and show how to use this metric of importance of each value that is related somehow to the WAIC incoming videos. So this is a very quick passing to over the large and complex ideas of model selection, in which I refer to the basic problem, the principle of parsimony, that is the basis of model selection in both frequentist and Bayesian frameworks. The model selection in the Bayesian framework, the current ideas of model selection in the Bayesian framework, for which we had to talk about predictive, the posterior predictive distributions and the PP checks to announce them, to announce their use in coming videos, and then to refer to further issues of model selection in the Bayesian framework. I hope you found this video useful, and I thank you for your attention.